In this video, we are going to go over general characteristics of matter. Chemistry is the study of energy and matter. When we look at a periodic table, it represents all the elements that are in the universe. In fact, if you go out to distant stars and planets, you're going to find less elements because on Earth we have created more elements. Matter can be classified as solid, liquid, and gas. A classic example is this iceberg in the ocean water. So we have the ocean water is the liquid phase. We have the ice, which is the solid phase. And then above the ice and the water is the water vapor. So we have all states of matter here. Notice that the molecule doesn't change. So it's still H2O, two hydrogens, one oxygen. But we see that in the ice, it's more of a crystal structure. In the liquid water, it's more jumbled, but the molecules are close together. And in your vapor, the molecules are further apart. The composition of matter, we can classify it into pure substances or mixtures. So let's first look at pure substances. Pure substances are separated into elements and compounds. In an element, you only have one type of atom, and the atom will be all the same. In compounds, they are composed of elements that are bonded together. So we see water here again. So we have two hydrogens and one oxygen bonded together. Through physical processes, you cannot separate the hydrogen from the oxygen in the water molecule. So a compound is classified as a pure substance because I have the same grouping. These are all H2Os all together. Let's look at mixtures. So in mixtures, we can classify them as heterogeneous or homogeneous. Heterogeneous is most things in our world. When we look out and see a pizza, we see the sauce and the cheese and the crust, and there's differences. Or we look at a rock and we see the color differences. In this example, we have wet sand. So we have water mixed with the sand, and you can mix it up, but given time, that sand will separate from the water. So heterogeneous mixtures, if they are liquids or solid, they don't stay mixed. And that's because the particles are so large, they will drift to the bottom of your mixture. Another example of a heterogeneous mixture would be paint. So you can mix it up, but it doesn't stay mixed. The particles are large, and given time, you'll have layers of paint with the different things that go in to make the paint. Let's compare that to homogeneous mixtures. These are also known as solutions. And I can have solutions in the liquid phase, but also in the solid and the gaseous phase. When we look at a homogeneous mixture or a solution, we see that it's mixed evenly. Oftentimes, if it's a liquid, you're going to see that it's clear. It can have some color in it, but it will be clear and it will stay mixed. So that Gatorade that you put on the shelf 2 years ago, it's going to stay mixed. It's not going to separate out. And that's because the particles that make up the Gatorade are small, and because of that, they stay mixed. So here we have some sweet tea, and we have the sugar molecules, which are quite large, but we have the water molecules there. They're still small enough that it will stay mixed. This is a chart that shows the relative abundance of the periodic table, or the elements that make up the periodic table. So in our Earth, we see that there's a lot of hydrogen and carbon and oxygen and nitrogen. So those things that help make up life on Earth. But we also see some heavier metals such as sodium and potassium and calcium. So these are more abundant than some of the other metals. So when we look at an element is made up of unique atoms. They are the building blocks of matter. When you compare a hydrogen atom to a helium atom, there's a difference. And when we go to make the periodic table and to make our lives easier, we have abbreviations. So the symbols of the elements you will see on the periodic table. So usually they just take the name of the element and they abbreviate by the first letter. So hydrogen is our first one, and the abbreviation of that is H. When we come to helium, because H is already taken, then they add an E. So helium is H and then a lowercase e. And the capitalization is important. So you don't write in all caps, and you shouldn't write in all little letters. So the first letter is capitalized, the second letter is lowercase. And some of the abbreviations don't make a lot of sense. For example, gold is AU. And that's because they take the abbreviation from the ancient name. So gold was known anciently, and it comes from the word arum, which means gold. And some of the other different ones there are silver, which is Ag, potassium is K, and lead is Pb. Some elements cannot exist by themselves. They always need to be bonded to another atom. And as an element, it will bond to itself. These are the 7 elements that are diatomic. And that means that, again, they always have to be bonded to something else and they can bond to each other. So when we go to write the symbol of nitrogen, we don't just write an N, we write an N2. To help remind you of all the elements that are diatomic, there's a silly saying here. Have no fear of ice cold bears like polar bears. Hydrogen, nitrogen, fluorine, oxygen, iodine, chlorine, and bromine. Also, there is this mnemonic, Brickelhoff. So again, when you say hydrogen and you're writing the symbol, you don't just write H, you write H2. And this would be if we're doing equations using the elements and seeing how they react. The periodic table is separated into metals and nonmetals, and the dividing line is found right here. It's a stair-step line. There's some argument about what it looks like down here at the bottom, and because there's disagreement, you will never get a question from me or the AP board about these elements down here at the bottom. Instead of having the stairs all the way down, some people think that it should just go straight down with these heavier elements. So who knows? So again, there's some controversy here, but you should know that metals are over here and non-metals are over here. Notice that most of the periodic table, they are metals. Hydrogen is kind of an oddball and it's stuck over here, but you need to remember that it's also a non-metal. There are 6 elements that hug this stair-step line, and they're called metalloids. So they have characteristics of metals and nonmetals. So they're kind of the tweeners. And so you should know these. So boron, silicon, germanium, arsenic, antimony, and tellurium. Aluminum is an exception. It has 2 sides that hug this line, just like the other metalloids do, but because it's so metallic, it is classified as a metal. So even though it's hanging out there with boron and silicon, it is not a metalloid, it is a metal. If we take nonmetals and we bond them together, we get what's called a molecule. Typically, a compound is a metal and a nonmetal bonded, and a molecule is just nonmetals bonded. And they are sharing electrons. And we're going to go into a lot of detail this year about molecules. This is just a little introduction. Here's some common molecules. We have water, H2O. Remember, hydrogen is a nonmetal, even though it's hanging out with the metals on the periodic table. Ammonia, NH3, and methane, CH4. Compounds, just like I said before, are a metal bonded to a nonmetal, and they make this crystal structure right here with metal, nonmetal, metal, nonmetal, metal, nonmetal. How they stick together is instead of sharing electrons like molecules do, they will transfer electrons. So metals lose electrons to the nonmetal. This creates a difference in charge, and just like a magnet, plus and minus, they will stick together. Now, as far as compounds go, if I were to take this crystal and crush it, I would never separate a plus from a minus. They would stay together as it's their own little unit. So this is a pure substance. It's just composed of 2 elements repeated over and over and over in the crystal. Some elements combine into compounds with different ratios. For example, I can have Fe2O3 and I also can have Fe3O4. So iron and oxygen can make that crystal structure, but with different ratios. And this is the one of the things that Proust studied around 1800. And you don't need to know names, you don't need to know dates. But he was wondering if you took water from a glacier or water from a lake, would it be the same substance? Would it be the same molecule in this case? And he was able to determine that water, no matter where you get it from, is always this ratio. 11% hydrogen and 89% oxygen. So let's look at this problem. It says, which of the following is the same compound based on the percent composition? So you're given the amount of grams of each of the elements, and then you're going to determine the percent composition by adding together the amounts to find the total, And the total here is 1.80 grams. And then you are going to find the percent by taking each of the components and dividing by the total. And you want to multiply by 100 to get the percent. I always forget to do that until I'm doing it. So when you do the math, you have 70% iron on this one and 30% oxygen on this one. Let's compare it to the next one. Are they the same compound? Because I still have iron and oxygen. So we're going to do the same thing. We're going to add them up to get the total. And the total we get is 0.72. So this is just a little simple formula. Just like figuring out your grade percent in a class, it's the same way. Your points divided by the total points times 100. This gives us the percent composition. So on this one, I get 78% hydrogen. So on this one, I get 78% iron and 22% oxygen. So comparing A to B, we see that they're not the same, and that's because their percentages are different. So I would have one be the Fe2O3 and one be the Fe3O4. Let's look at C and D. Let's see if we have any that match, or maybe they're completely different. Some other formula. So again, find the total, and then we'll divide. And when we divide, we find on C, we get 70% iron, and we get 30% oxygen. So we see that C and A are the same. And if I look at the last one, I find that I get 78% iron and 22% oxygen. So we have B and D are the same. So in the 1800s, trying to figure out if compounds are the same, you can use percent composition and look at the percent quantity by weight of each element to compare different substances to see if they are the same. Let's talk a little bit more about mixtures. Again, mixture is a combination of two or more pure substances. I could take two elements and mix them together and have a mixture. The classification as far as mixtures go is heterogeneous versus homogeneous. Heterogeneous, remember, they're mixed unevenly. You can see differences. There's colors. There might be phase changes, like a glass of ice water is all the same molecule of H2O, but because I have water as a solid and water as a liquid, then it's not uniform. Homogeneous mixtures are uniform, they stay mixed. You can have solids. So for example, my wedding ring is a combination of gold and silver and other metals, and they melt it all together. But those metals don't chemically combine, they're just mixed. So you could take my wedding ring and melt it down and separate it into the different metals. A synonym of homogeneous mixture is solution. So when we talk about solutions, we're talking about these uniform mixtures. Classify each of these as an element, compound, or mixture. So stop the video and then we'll come back and see if you got it right. Okay, we're back. How did you do? So looking at the first picture, those little swishing signs, that is showing that they're moving. So these are all gases. Notice that they are different gases. We see that they are not chemically combined. This is a mixture. And because they're all the same phase, I would say it's a homogeneous mixture, but it didn't ask that. It just asked mixture or not. Looking at the second one, I see the same thing. It is composed of more than one element, so this is a compound. In 3, I only have one element, and so that's just my element. And then 4, I do have the same color, so that's representing the same element. And this is a diatomic element, so don't be fooled with this. It's not a compound. A compound would be two different elements, so like oxygen and hydrogen. 5 is trying to show that this powder goes into this beaker with some water. So this is a solution or a mixture. And I see color differences here on this one, so this is a mixture. So it's not an element, it's not a compound. So an element, you're going to see it's all the same, like these little red dots here, or it will be found on the periodic table. So if you have the name of something, and if you're wondering if it's an element, it should be on the periodic table. If it's not on the periodic table, then it's not an element.